Hello and welcome to 33rd lecture of course on data-enabled tribological engineering from experiments to predictive model. Topic of this lecture is uncertainty, quantification and sensitivity analysis. We have learned something about tribology, something about machine learning. Then what's the point to learn something about uncertainty? In my view, uncertainty quantification and sensitivity analysis play important role. Reason being we need to choose right equipment and right method to analyze the tribal systems. By quantifying uncertainties, decision maker like us can take very good informed decision or informed choice. So, present lecture provides a broad overview of uncertainty quantification and sensitivity analysis. But we will be touching only on the concepts and their practical application. We are not going to cover this topic in a depth. Sensitivity analysis, to some extent, we have involved, or maybe say we have covered in previous few lectures. What is the major reason to involve sensitivity analysis is to find out what is will be the variation. If there is some variation in input parameters, how it will influence output. Is something like we have done PCA, but it is slightly different than PCA. In the situation we are trying to explore, and we can go ahead with changing one parameter at a time and figure out what will be the output variation, or we can go ahead with kind of ANOVA analysis, go with a factorial design and figure out what will be the impact of different parameters overall output. In addition, there is something called a global sensitivity analysis, which involves almost all parameters simultaneously. However, in the present course, we are not going to cover the global sensitivity analysis, which is required, but it requires little more depth. So for this lecture or in this course, we will not be covering those. Let's start with the uncertainty. Looks very not necessary kind of thing, because we are talking about machine learning and we are talking about some sort of very good accuracy, and still we are thinking about uncertainty. So why we think about uncertainty, we say very clearly every measurement, whatever we measure, it will deviate from slightly from a true value. That means whatever the true value will be deviating to some extent. Let's take a very simple example. We have this scale, this side is inches, this is an mm. Now, if there is some sort of quantification, we say 0 mm, 1 mm, 2 mm, 3 mm, 4 mm, 5 mm. What will happen to 4.5 mm? We cannot measure, and there will be deviation. Now, if some number is something like a 4.5 mm, and we can measure either 4 mm or 5 mm, so there is some sort of uncertainty in this 4 to 5. Even there may be deviation. One person may read something like a 4.5 as a 4, other person may read at a 5. So again, there is an uncertainty. So that kind of deviation will be there almost in every measurement. Let's take an example of this kind of a scale. When we are measuring the mass, and resolution of this scale is supposed to 1 milligram. That means I cannot measure value lesser than 1 milligram, or something like we will have a quantification 0 milligram, 1 milligram, 2 milligram, 3 milligram, 4 milligram. What will happen to the 0.5 milligram, or what will happen to zero point 0.6 milligram? We cannot measure. So there will be some sort of deviation from actual value. Actual value may be 0.5 milligram, but we will be measuring something like either 0 milligram or 1 milligram. We cannot measure zero point 0.5 milligram because we have a constraint on equipment itself. So that's why we require uncertainty analysis to figure out which kind of equipment I really require, because there is a variety of equipment available. So we need to think from that angle. And if we try to give formal definition, we say uncertainty is a range of confidence levels. We say confidence level 90%, 95%, or sometimes we say the sigma, 1 sigma, 2 sigma, 3 sigma. Now that is going to be a kind of errors, or that can be treated as a errors. And many times we use a word measured value, that maybe many times we use a mean value plus minus uncertainty. We measure something 0.5 plus minus 0.01, something like this. So there is uncertainty. Now this uncertainty is defining whether we are going for the normal distribution, Gaussian distribution, or some other distribution, or some sort of a distribution. So that will depend heavily how our solution come out. And when we are trying to say we are matching actual cases or actual result with the predictive results, in the situation uncertainties really play a very important role. Let's take another example. Here we wanted some shaft diameter, and shaft need to be turned on a lathe machine. We took around 34 specimen or samples. We wanted a nominal shaft diameter as a 4.5 mm. But when after 34 samples were finished, we found the mean value of this shaft is a 4.58. Naturally, there is some variation, there is some error. It's not matching 4.5 mm, we are getting 4.58. And there is some sort of standard deviation also. How do we find a standard deviation? We know very well that is a formula, the statistical method, and we know how to find out this. It is available in MATLAB, it is available in Excel sheet. We have all the details, we can use this formula, I can figure out. Again, our assumption is a normal distribution. That means when we plot it, we'll find the major diameter in this situation and what is the frequency, how many shaft diameters are coming in the range. And again, these are the solution accuracy 4.57, 4.58, 4.559. That means again we have some sort of uncertainty in the measurement also. If we go for more finer one, the variation will come. And these are the real practical cases. Even though we have machine learning, we cannot increase accuracy unless we go for the better equipment, better machinery. So many times it provides some sort of innovative thinking. We wanted to achieve something, but because of the lack of equipment or shortage of the sensors or some sort of measurement technique, we are not able to achieve. And there is a gap, and we need to really make that kind of setup. So this is important to understand. Now, as per the ASME standards, this uncertainty has been divided in two parts. What they say is called a systematic error, other one is a random error. And mostly we think uncertainty from a random error point of view. Reason being systematic error can be corrected, that is well under our control. However, this random one will not be under control unless we change equipment, change the measuring technique or process. So this is important. Random errors may not be easy to remove, but systematic errors are possible. So again, when we go inside the depth of the uncertainty, we are able to figure out which are the systematic errors, which are the bias errors which can be removed. And how do we define? The true value is something like this, and we are getting mean value something this. So in this case, the true value which we wanted a 4.5 mm, but we are getting deviation 4.58. So if there is some sort of alignment problem, is there some sort of a variation or some sort of systematic error, we should rectify it, and then it can be changed. That means systematic error can be easily changed, or maybe when we put efforts, it can be minimized. And most of the time in sensor, we get a calibration constant. We recalibrate whole equipment to come back to the zero value or bring the systematic error to zero value. So this is important, particularly when we are dealing with the sensors, when we are dealing with a system, where we are dealing with the subsystems. So what I can say, the uncertainty can be divided in systematic error and random error. Controlling random error is difficult, that's why we require more and more number of samples. Now in this case, number of samples, suppose 30, we will get some variation. Now if number of sample increase to 100, we will get a lesser variation, quite possible the mean, it will come to the real mean value. So that is a possibility. With increasing number of samples, we approach to the true value after removing the systematic errors. So this is important for us. I'm just taking another example. In this case, we have a tensile strength data, and then measured tensile strength is something like a 433 megapascal, 444, 54, 457, 470, 476, 481, 493, 510. So they are the 9 samples, and when we take a mean value, it turns out to be 468.67. This is a measurable, and standard deviation is only on slightly on a higher side. As the standard deviation on the higher side, we generally go ahead with coefficient of variation. And coefficient of variation on the higher side, naturally, either we have taken lesser number of samples and we need to go for more number of samples, or there is some sort of uncertainty which we do not know. So we need to go in the depth of that, and we need to explore, and then we go for the refinement of that. So it is important, coefficient of variation is important for us to understand. If it is on higher side, like more than 1%, 2%, where something is wrong, and then we need to really re-look into that. If we are using directly machine learning algorithms on that and assume that everything will be fine, no, that will not be. Reason being, we need to think from measurement point of view also. If measuring equipments are not sufficient, are not good, or fabrication facilities are not good, manufacturing facilities are not good, we cannot achieve the results. Many times we say domain knowledge is a must. Machine learning will help us. Artificial intelligence will help us. But without domain knowledge, that will not really give the good results to us. Now, this is what we have covered in the lecture 17. We were discussing something like ASTM wear test methods, and then we mentioned how the standards are made. They give to the different labs, as well as ask each lab to conduct the number of experiments. And we found that within a lab itself, a COV, particularly for wear, was high. In this case, is 8.9%, it is a 20%. Coming to the highest in this case, 17.9, while coming to the between lab is 29.3. So here they need to dig out what are the really reason for this. Is it environment affecting a lot? If it is, do we require some sort of different calibration constant? So it is important. Or we require more controllability on the parameters. So parameters already we know that's some sort of rotation, forces. If are we able to really control more on a force, what should be resolution on that? Or maybe the angle of incident, angle of attack, what should be resolution? So those equipments also need to be accounted. What should be the resolution accuracy, and so that we get a better and better or results, obviously minimum to minimum COV. However, here in this case they write a COV, sometimes people write a CV, that's a coefficient of variation. We need to keep minimum so that we get a better and better accuracy, a better and better reliability, a better and better predictability. So if there is a uncertainty, degree of predictability will decrease. Whatever the machine algorithm I use, it will not give me good results. So measuring, and moreover second is the data, number of data which we have, or really they are good data. Do we have sufficient denoise, or we have removed all the noises or not? We do have a number of filters, but without domain knowledge it will not really help us. Let's take another example of the source of errors. We say in case of the systematic errors, we find many times a failure happen because of that, and it creates a lot of uncertainty also. So one kind of uncertainty has been shown over here. Measurement is should be 19.70, but we are looking from a different angle. So sometime we are getting 19.82, sometime we are getting 19.62, and we are not going with the parallel to the accurate results. So parallax error is being mentioned in this case, and that is often said either this is a human error, we take wrong results. Now this can be digitized, the errors can be reduced. Sometimes we have hardware errors. We say we do not really calibrate the equipment properly, and in the situation there will be hardware errors. So naturally, whenever we want to operate any equipment, it should be recalibrated, and then only we should take a results. Sometimes we have a software errors because of we, as I mentioned, is shown in a scale. we cannot measure accuracy better than 1. And then if you have done some measurement directly from a scale, and then which has a resolution of 1 mm, when you come to the software, it can round off or maybe give many decimals also. In both the cases, errors will be there, and that need to be mentioned. Last one in this case is a procedural error. Sometimes we do not really do proper arrangement, and sometimes the noise will come from outside. Like sometimes we forget EMI shielding, and that is creating a problem. Sometimes we use a wrong cables, that will also create a problem. So if possible, we try to minimize these error and the first go. Then we come to the random error and try to minimize random error, which is not in our under control, but we try to go ahead with the sensitivity analysis and figure out which parameter is really getting affected too much, even with a slight noise. If that is the case, then we'll go for the better accuracy. We can change equipment, we can change the measuring technique, we can go for more sophistication. And that is important because we are going to use the resources, and resources are costly. We need to take a decision or related to the cost. For that purpose, we really require a good uncertainty analysis of uncertainty quantification and sensitivity analysis. Let's take one example. In this case, this is the gear pair. Now in this case, what we are showing that there is a radial error, misalignment. You can see here that centers can be pushed little bit so that gear mashing can be proper. However, there is some sort of a radial misalignment. Maybe say little bit, instead of 50 mm, we are keeping something like a 50.1 mm, 50.2 mm. That can be corrected. Now second one is a axial. That means this axis and this axis radially they are fine, but because the phase width is not matching with each other, that means there is some sort of axial misalignment. Now other one is perpendicular. Now in this case we have in plane and perpendicular plane like misalignment. And misalignment is one of the major cause of the failure. It causes a major failures. So this can be corrected, and misalignment sensitivity towards load carrying capacity towards stress is very high. So the first thing should come be, we should align each and everything properly, and then only we do experiment. Many times we don't give a lot of weightage on a measurement, and then directly we take some reading and we try to give some formula or some machine learning algorithm and try to fit with that values. So everything will turn out to be garbage, because that will be wrong. So first emphasis should be given to minimize these errors. If these errors are minimized, then only the machine learning and artificial intelligence has some role. If there are the errors are here, we cannot do much better job. Now this is what we showed, the misalignment errors, and I'm taking example of my lab example, and then there is some sort of misalignment, and because of the misalignment, what will happen, the bearings will get affected, and the bearing is very sensitive towards the clearance or misalignment. Even 0.1 degree misalignment is sufficient to damage the bearing, and that has been shown over here. You can see that there's a taper roller bearing, the cone is got damaged, rollers are damaged, even our cages are also deformed, even the seal which was there, that also got broken also. So there will be major issue when there is a misalignment. Source of errors start from there. If we are able to align properly, we have a laser alignment tools. If we are able to align, then the things will be fine. If we take some reading out of this gearbox and we use a machine learning, what's the use? It is not going to give very good results to us. Now I have earlier delivered one lecture on bearing clearance, because I know the clearance is a very sensitive. It will affect the performance significantly. So this lecture is already available on NPTEL, and this lecture was given around 11 years ago, and then I find a good number of likes and many number of views on this. So if possible, please visit to this website and figure out how the bearing clearance plays important role for bearing performance. So what we say, the measurement, whatever we mention, it is not a single value. Sometimes people say measurement is single value. It's not a single value. It needs to provide some sort of range, and that range should be having some sort of confidence level. As I say mentioned, it can be a 1 sigma, 2 sigma, 3 sigma. Sometimes we give a range also, like in this case we have a range something like a 20.1 is a mean value and plus minus 0.1. What's the meaning of that? That means we want to aim to achieve 20.1 centimeter, but there's a possibility, or there's an uncertainty. The whatever we get output, it may range in a 20.0 centimeter to 20.2 centimeter. So there is a range. So again, measurement is, many times we are mentioning a single value. It is not really a single value. It has to be in some range. That is as is mentioned earlier in a scale, when we are saying the 0 and 1, if we mention something like a 1, may not be 100% correct, because we know it can be slightly lesser than 1, it can be slightly more than 1 also. So that is a range, and that is what we need to quantify. That's why we say uncertainty quantification is a must. What kind of equipment you are using, that should be mentioned clearly with the results. Now we revisit again. This slide was covered in lecture 25th, and we were referring to one paper where analysis of West Marble dust filled polymer composite, and then they perform experiments using Taguchi and ANOVA, and then they try to utilize a neural network. We mention also the specific wear rate, and then they measure these values. They have provided the value. Now they also provided some sort of uncertainty in a measurement. If you look at here, there is a upper limit and lower limit, upper limit and lower limit, upper limit and lower limit, upper limit and lower limit. Reason being, they are measuring, and then they found that when they are taking 3 readings, all 3 readings are giving different results. So naturally they need to mention here. Often the point means a mean value. This point means a mean value. This point means mean value. This point means mean value. Often this is done as one of the way to present the results, to present in a more meaningful manner. So they did. Only the question comes, they are getting almost equal distribution from a mean value. You look at the mean value, upper and lower limit are more or less same. Upper and lower limits are same. That means everywhere the SD, or maybe say standard deviation, or 3 standard deviation is same. That remains one of the major question. How do we get this kind of results? Mean value is 1 point, but variation upper bound and lower bound, and in all 25 cases we are getting similar kind of trend, which is very rare in my view. So that's why I kept this slide, extra slide. You can see here the 5 observation. You can see here the variation. Here the variation is a lesser, here variation is a more, variation is somewhat mid. So whenever you go for observation, not necessary every time variation will be same. When you go for the reading, if you are taking more than 50 readings, still there is a possibility variation may come more or less same. But if you are taking 3 observation, I am sure sometime will get a huge range, sometime will you get a lesser range. It cannot be same for all 25. So that's why we, for better clarity, we need to mention what is a really error bar, how they quantify, what is a confidence interval, whether they were mentioning about a standard error or some sort of standard deviation. So that need to be mentioned very clearly, right? So that we get a better and better understanding what we have mentioned in this case. So I have shown one typical example here, the range. Nothing is mentioned, we'll treat this as a range. What is the meaning of range? This is upper limit, we are getting upper limit, or and then here this is a lower limit. That means minimum value and maximum value, and we need to find. Nothing is mentioned, that means the range. And sometime we write the dot, that will give the mean value, and the top one will the first standard SD, the standard deviation, and this is a lower standard deviation, that means plus minus 1 SD. What is the meaning of plus minus 1 SD? Is something like they are providing a confidence level of 66.7%. Approximately the 66.7% of data point will fall within the range of this 1 SD. Now instead of 1 SD, if they go ahead with a 2 SD, then it will be the 95% of data will come in that. If nothing is mentioned, as I given the range, that will be plus minus 3 sigma. That's what is generally a trend. So if nothing is mentioned, we will treat as a range, that means plus minus 3 sigma. If this is a given, and now maybe they have labeled it or they have shown it on the itself figure, or maybe say use a legend that it is a mean and standard deviation, then it makes sense. That means interpretation is much easier in this case. So what are the steps when we go for the uncertainty analysis? We need to figure out what are the source of uncertainty. In previous one of the previous slide, I showed the 4 main sources, and that is a particularly to minimize the bias, not a random. Reducing the random, we require some extra thing. After doing finding the uncertainty, now if there is an uncertainty related to humidity, related to temperature, we need to find out. And sometimes we really require a sensitivity analysis. Now if some parameter is heavily depending on the temperature, or the corrosion rate is heavily depending on humidity, that sensitivity need to be figured out, so that we can keep a little more control. It will turn out to be little costlier, but it may give better predictability. So wherever the cost comes, sensitivity analysis is going to play an important role. Wherever resources allocation comes, sensitivity analysis is going to play important role. So identification of the sources is the first thing. Then comes the quantification. We can do a statistical analysis the way we have mentioned, or we can do a Monte Carlo simulation, which we are not covering in the present course because this is a separate technique. And as I mentioned, the sensitivity analysis can be done. Reason being to find out what will be the range and what will be the upper limit, lower limit for that. One additional point comes something called error propagation. How uncertainty in one variable is going to affect outcome is a point, but how uncertainty of one variable will together with other uncertainty of the variable affect the results. Just to elaborate that, I am providing this table. We say here the 4 operation: addition, subtraction, multiplication and division. Here we are assuming x is a one variable, y is another variable, and z is the output. And here we are also saying that z x is also varying, it has an uncertain range, y is also varying, it is some sort of uncertainty. Similarly for subtraction case, similarly for multiplication case, similarly for division case. Just to understand a little bit better, let's consider some sort of values. We say x, in this case it is something like a 2.3 meter plus minus 0.2 meter. Y is a 3.2 meter plus minus 0.1 meter. And what will be the z value? Naturally, in z case, we need to go ahead with what is the mean value and what is the uncertainty or standard deviation. So we need to multiply. If you go ahead with the multiplication case, so we will choose this case, x bar, that's the mean value, the 2.3 into 3.2, multiplication will turn out to be 7.36. Coming to the standard deviation, because we need to write or uncertainty, we need to write about this. So here it is given a 0.2, here it is given 0.1. So 0.2, 0.1, x has been given as 2.3, y has been given, y bar has been given 3.2. We need to find, and then the 7.36 is will be multiplied with this value. And if you multiply, this value should come something like a 0.68. Now this is important. Now question comes, how do I know this is a standard deviation? Because unless it is well specified, we cannot get at this value. Even though if it is not mentioned whether it is a sigma d or 3 sigma d, doesn't matter, because we are going to present in the same format. If it is a sigma d, we are directly calculating sigma d. If it is not, we have to divide by 1 by 3, and we are multiplying this by 1 by 3, and initially we are dividing and finally it will be multiplied. So again the value will be same. So whether it is a sigma d or 3 sigma d, results will be same. It is not going to change. Even though it is not mentioned, results are not going to change significantly in this case. Now second case is the division case. Here z is given as x by y. So we will be using this formula, and we can figure out the z value is something like turning out to be z bar as a 0.72, because 2.3 divided by 3.2, it will turn out to be 0.72. Now because this value has come down 7 instead of 7.36, it is a 0.72, almost 10%. We will find that this standard deviation also is turning out to be only 10%, and that's why it is coming as a 0.07. Now here division is reducing the uncertainty, multiplication is increasing the uncertainty, and that is what we call error propagation. When we have more number of parameter, this propagation will happen. So whatever the input we are giving, and if it has an uncertainty and we are driving a relation from that input, or maybe there, suppose there are many variables, then error will be huge. Is it a justifiable? Is it a fine? That we need to figure out. And if you want to minimize a main error, then use a sensitivity analysis, go ahead with a better equipment, go for better measurements, go ahead with a better recalibration. Now coming after that, we need to also write the bounds and what is the interval. Sensitivity analysis already been mentioned. Finally, we need to communicate the results in error bar. What is a really lower limit or upper limit or mean value plus minus SD, that needs to be clearly mentioned utilizing all the results. Let me define again the sensitivity. What we say, sensitivity analysis assess how changes in input parameter affect the output value. This is important. Why we are doing it? Because we know there may be even 72 parameters. Are we going to do uncertainty analysis for all 72 parameters? No, not necessary. The way we have mentioned that we can utilize the PCA, the sensitivity analysis is similar kind of thing, and we say no, only the 5 parameters are very sensitive, they will affect output heavily. So we'll be doing more detailed analysis of those 5 parameters. If those 5 inputs require very refined in measurement or quantification or modeling, I'll be doing that. I'll not go with all 72 parameters. If some parameter, after doing elaborative calculation using the finite element, boundary element method, is going to affect the output only for 1%, why shall I do that? But if we have input variation is a 0.1%, but output is going to get affected by 1%, naturally I have to correct 0.1% also. So that is important. That's why we use a word. They are the key parameters or sensitive parameters. Then previous slide or previous example, I use a word clearance. Bearing clearance is very sensitive for the bearing performance. We cannot avoid it. Bearing clearance has to be maintained properly. Installation of bearing need to be done properly. If it is not done, results will not be favorable. So what we say, it is a really giving a relationship between input parameter and output parameter, identifying the significant impacting parameters, or maybe say key parameters, sensitive parameters. So it is very important to understand. So I'll again refer my earlier paper which we have discussed in earlier one of the lecture, multi-object optimization of journal bearing using the Pareto optimal friend, where we try to figure out sensitivity of the radial clearance, oil viscosity, and length to diameter ratio. These are the input. So clearance is the input, oil viscosity is input, length to diameter ratio is input. What is output? Is a power loss. What is another output? Oil flow. So there are two output, and we are trying to figure out what will be the sensitivity of the radial clearance, what will be the sensitivity of the oil viscosity, what will be the sensitivity of the length to diameter ratio. This is what we did in earlier lecture. Now I'm just trying to repeat the same slide so that we have a better understanding of the what we are trying to do. So in sensitivity analysis, what we say initially is a power loss. We covered a radial clearance. We say length to diameter ratio, viscosity. We consider three levels. We say 40 to 45 micron, 50 micron, because maintaining even the 10 micron clearance is difficult. We require a good alignment as well as a manufacturing. But now, if this power loss contribution is only 0.2%, so now if bearing clearance is a 40 micron, 45 micron, 50 micron, power loss is not going to get affected much. But if possibility, other parameters. But if I'm looking only from power loss point of view, I say no, this parameter is not that good. We don't have to go for the more close tolerances, or we don't have to really go for better fabrication facility. But if it is on the load, then we will see whichever output which is a desirable output, will not need to focus on that. Coming to the second parameter, the L/D ratio contribution is 10.8%. Coming to viscosity, contribution is significant, 89%, and this is a key parameter, is going to affect a lot. Slight variation in viscosity, that the modeling of viscosity, choice of the selection of viscosity need to be given a lot of emphasis. If there is some problem, power loss will increase, coefficient of friction will increase. That is need to be accounted properly. Now coming to the side leakage. Now in side leakage, clearance has a 17% weightage. So question comes, am I giving more weightage on a power loss? Am I giving more weightage on a side leakage? Now this is to be decision making. If decision making team says power loss is more important, then clearance will not be much problem. And decision making team says that minimum threshold for the load carrying capacity should be this, then we need to add that also as one of the major constraint. So this way we try to do optimization. Now coming to L/D ratio, side leakage doesn't have much impact, is a 0.17%, which is almost negligible. So if I see power loss and oil flow, this side leakage L/D ratio is not really affecting significantly. So now L/D ratio is 0.5, 0.55, 0.6, 0.65 is not really affecting much, particularly for power loss as well as for side leakage. Now coming to the oil flow and viscosity, again we find this is a key factor. It is a 82.75% effect. That means overall viscosity is going to play very important role. So whatever I do modeling, whatever I do INN method, or whatever oil I choose, I have to give a lot of emphasis on the viscosity. Any relation, any prediction related to viscosity need to give a maximum emphasis, so that overall results are as per the what we want. So what we say, primary goal of the sensitivity analysis is to find out the input parameter or key parameters which are really affecting the output model heavily. And second thing is that many times we take a decision, how do we do the kind of the modeling. Like earlier we took this kind of Reynolds equation and we say the side leakage may be neglected, so then this term will be avoided, or we say the axial direction can be avoided, or we say that squeezing is not going to affect, it can be avoided. But if I do a sensitivity analysis and I find a slight variation in this term is affecting output heavily, then I need to account that even in my model. Otherwise not. Now in this case, as a viscosity is playing very important role, that means any negligence in a viscosity modeling is going to affect a lot. So that will not be justified. Now viscosity is playing very important role on affecting the side leakage. It is playing very important role to increase or decrease the power loss. So that means viscosity needs to be accounted properly. All the modeling need to be done appropriately. If we are not doing, then it is not justified. So what we say, sensitivity analysis are often used in conjunction with uncertainty analysis. If I have some variation, what will happen? So that is what we say. That's why uncertainty quantification and sensitivity analysis must be done together. So to understand the system better manner. However, there are many methods available. Few people use a sensitivity coefficient. We are not going in that kind of detail. So that somebody says sensitivity coefficient of all parameters are like this. We want to rank all the parameters, and then based on that we choose it. So this is also possible, and in tribology it will play very important role. However, in the present course we are not covering that. Now coming to the uncertainty quantification or sensitivity analysis in a machine learning. So I'm just again repeating the one up slide which I covered in the lecture 24th. We try to model one matrix, what we call a confusion matrix. We tabulated actual value versus the predicted value and try to quantify this kind of uncertainty into the four terms. We say we want to find out accuracy, we want to find out the precision, we want to find out the recall, and you look at the recall is also known as a sensitivity, and one is a one f1 score also. So there are two things here. One is a precision, what could be, and second one is a recall, that's a sensitivity. We require both, and this was measured using the this kind of a confusion matrix where a predictive negative, predictive positive, actual negative, actual positive were compared. Here we got 100% that whatever we predicted and actually it was a negative, and here we also found everything fine. Diagonal cases we find this is a fine, and off diagonal we find there is a some sort of a false negative and false positive. So this is important. Now we try to give accuracy, and we say instead of positive negative, if I say class 1 and class 2, we can figure out similar manner. You can see here the correct positive, in this case a correct positive related to class 1, correct positive related to class 2, and here is a wrong positive for class 2, wrong positive for the class 1. Now in this case accuracy is also being given a similar manner, because when we go ahead with accuracy, we say true positive, true negative. That means we have measure 100% correct results. Whatever the positive, whatever the negative, we actually measured and we actually identified, our algorithm actually identified that manner. Our machine learning algorithm actually identified that manner. And total attempt or total number of trials. That's what was been done. However, coming to the precision, we are looking only in the true positive, and whatever the positive were found, but false positive as well as true positive together. Coming to the sensitivity, here again the positive what we have been mentioning, but here we are also talking about not only the true positive, but what are the false negative also which we categorize. So there is just only one term difference as the false positive and false negative, and both together we need to work. So we need require a precision, we require recall or sensitivity analysis to get a overall good impression or bad impression related to machine learning algorithm. And this is here what we are showing for class 1. Precision can be given because we are trying to figure out that this was actual positive or actual class 1 whatever we detected, and but in this case is a wrong that has been given over here. Coming to the class 2, same thing, this is the correct one, and then we found a negative in this case. So this is important. Coming to the recall case is a similar manner. We count this is a right and this is a wrong. This is a class 2 case, this is a right, this is a wrong. So this is a what we need to figure out. Now in this lecture 24th we try to classify this weird debris in 5 classes. We did a similar kind of thing. Overall model precision we calculated something like a 95.61%. Overall sensitivity of the model we covered something like a 95.92%, and then accuracy was defined using the this kind of confusion matrix which were also mentioned. And then we say wherever we are able to train it properly, because of our understanding results will be good. And we were 100% sure related to spherical particle, we were 100% sure related to cutting particle, because cutting particle aspect ratio need to be very high. Spherical shape is something like that, we can measure easily. However, there was some sort of confusion only in fatigue and sliding, and sliding and rubbing. So precision rubbing is giving good results, but fatigue and the sliding case we were not getting good results. Coming to the recall, In this case of fatigue, again the problem. However, for spherical we are getting 100%. For cutting, again we are getting 100%. So major issue came only in fatigue and sliding and rubbing. So that's what need to be accounted. Assuming we'll get 100% of the accuracy and 100% precision, 100% sensitivity, will not give a good result, because that will turn out to be overfitting. So somebody is aiming for 100%, something is wrong. We should not aim for 100%, but very high value is good, because 100% means overfitting. Slight change, predictability will reduce, and my future forecasting will be reduced. So we should not aim also 100%. So we can classify in this manner. We say high recall and high precision. This is a perfectly handled. That is a fine for us. High, we can set a limit 0.595, 0.96, 0.97 is up to us. However, low recall, like in this case, we found a low recall 0.83, but high precision. So we are not able to classify properly, that we are not able to put in a proper way. However, whatever we are predicting, that is a trustable. Coming to the high recall but low precision, we say we are able to find out the classes appropriate manner, but we are also including other classes. So this is important to understand. However, low recall or low precision, something is a majorly problem, and then we need to go ahead for the refinement, improved in measurement accuracy. So many times this kind of exercise helps us to revisit whatever we have done. So what we say, many times we do sensitivity analysis and uncertainty analysis together. A reason being, these both are the techniques to understand the behavior and reliability of the model or system or experiments, and then also find out what will be the variability and what will be the impact of those variability on output. So both are important. So sensitivity analysis is important to understand. Uncertainty analysis is also important to understand for us. And then if I want to say in slightly different words, I say the sensitivity analysis helps focusing on uncertainty analysis. I should not start worrying about each parameter too much. First, sensitivity analysis should give me whether that parameter is really affecting output majorly or not. If it is affecting majorly, then uncertainty analysis in detail will be required. So these two, both the techniques are important to understand, so that overall the decisions are done properly, and then whatever we take decision in, those are results are the robust, reliable, as well as we are able to figure out what are the limitation of models, which we can think about in future. So it is basically better informed decision, and it's going to improve the model performance. So that will be important. Now coming to the tribology, we say understanding uncertainty related to tribology. And tribology, almost everything is uncertain. So almost everywhere uncertainty you will find. And what is the sensitivity of the surface roughness is huge. That means surface roughness cannot be avoided. And there we really require accurate measurement, so that overall friction is predictability increases and wear predictability increases. Unfortunately, maybe say 10-15 years back, people were not giving a lot of emphasis on surface roughness, but now it's turning out to be very important. Coming to the material hardness, or maybe the surface hardness, again sensitivity is a reasonable, and uncertainty in a hardness measurement naturally will affect the wear resistance or impact on the wear. Coming to the operating condition, we need to have a control on a temperature. Sometimes temperature change in a temperature from 0 to 60 degrees not affecting performance, but from 60 to 70 or 70 80 degrees affecting a lot. So we need to know what will be the lower limit, what will be the upper limit. So this is also causing an uncertainty. So uncertainty related to surface roughness is huge. Our impact is huge. Material hardness also reasonable. Operating conditions also need to be considered. Again, coming to the lubricant, variability in a viscosity really plays important role, particularly in a hydrodynamic and elastohydrodynamic analysis. If we are going with a boundary lubrication, mixed lubrication, it may not play a major role. However, film thickness will have always very high sensitivity, or maybe say uncertainty will be impacting us. So that is also required. In these days we try to do all surface treatment or coating on the surfaces, because we know bulk material doesn't play much important role in tribology, but surface treatment or coating is going to play important role. So what should be the thickness of the coating, that also need to be optimized. So again, this I will be related to uncertainty. Experimental errors, yes, it is really going to affect a lot. So we'll be covering one example where experimental measurement is playing very important role. Contact geometry, yes, it is playing very important role. Whether it is a convex shape, convex concave shape, flat shape, these are also important. To some extent, vibration and impact, the loading also will important for us. How to really address this uncertainty? We should say that we require a good experimental testing. Without testing, without experimental work, we will not be able to really justify. We really require advanced modeling techniques. Of course, as I mentioned, we have many variables, and which term need to be kept and which term need to be neglected, or maybe say assumption can be taken to simplify or reduce a linear equation, will depend on the sensitivity analysis. And then whether we really require more and more improved measurement technique. Shall we go ahead with pin on disk machine, or shall we go with SCM? Shall we go with the TM? Shall we go with AFM? This can be really checked. It's not necessary for every case we move to the AFM, every case we move to the SCM. It's not necessary. So understanding is important. So that's why we say if we have a good domain knowledge, good understanding of the system, then it will help. If we don't have early some machine learning, and when we are going ahead with the uncertainty analysis, it will try to give us some sort of novel thinking to us, so that we try to understand the system proper way, and then choose a parameter, choose a variable, choose a measuring equipment. Coming to the sensitivity analysis, as I mentioned very clearly, surface roughness plays very important roles. Material hardness plays important roles. Now, sometimes Young's modulus plays important role, particularly for elasto-hydrodynamic lubrication. It may not be very important in other cases. So we need to know what is the really lubrication regime, and in that lubrication regime, whether elastic modulus is playing a role or not. That is very important. As I mentioned, the lubricant viscosity. Again, if you are going for the HL case or EHL case, it will play important role. Otherwise, the lubricant additives are going to play important role. So in one case, hydrodynamic lubrication viscosity will play a role. Elastohydrodynamic lubrication viscosity will play a role. Coming to the mixed lubrication, lubricant additives will play important role. Mixed lubrication and boundary lubrication, lubricant additives are very important. The temperature environment, it would going beyond certain range, like a temperature above 60 degree, above 80 degree, above 100 degree, naturally the sensitivity of that will be very high. So it cannot be just a linear, it will be following non-linear or bilinear, and then suddenly there will be sharp increase. So those things are important. Surface treatment, and similarly the velocity. Sometime in case we have a EHL case, we know the sliding impact velocity will have more impact compared to the load itself. So then the velocity will play more important role compared to the other parameters. Now, when we think about optimization, and sensitivity analysis is the initial part of that. So sensitivity analysis becomes a crucial for the design reliable and efficiency of the components, and then we try to understand the system properly, and it will really help us to understand properly, or it provides a deep domain knowledge. It makes us curious to understand the domain knowledge, because domain knowledge plays very important role. If I learn only machine learning, if I learn only artificial intelligence, and I think I will be able to solve the tribological problems, no, it will be very difficult, because without domain knowledge it is not. So we will be taking one example where we are, when we are using a domain knowledge, domain equation, how the accuracy is improving, uncertainty is reducing. That's important. So we'll be covering two examples, maybe those are both are published papers already of the other authors. I'll cover those papers so that we have a better understanding of the system. So first paper, which was published in 2022, Tribology International, they try to use a word of wear volume evaluation, and then they give a little more emphasis on a topography based method. So I'm just trying to give justification for that. Already we have covered in the fifth lecture, of which was on wear measurement techniques. We already said that weight measurement may not be a very good option. Volume measurement will be better option. And we mentioned very clearly, if we are able to move to the area where the material has been worn out and able to really capture irregularities, asymmetry in shape, it will give the better results. And this paper is also giving the same kind of conclusion. So it is important for us. Just for a little more clarity, we covered something like a 4-ball test, and then we say after 4-ball testing, when you do, you will get some sort of wear scar, and wear scar diameter can be given as a D. And then if you use a mathematics, we can find out the wear volume. Now here wear volume is indirect, it is not direct. We are not directly measuring wear volume, we are measuring the wear scar. And after measuring wear scar, we are assuming it's a flat, it's smooth. Every value of H is same, but in the real case it is not. This is a what you can see here, that variation everywhere, value of H is not same. That is, H is a kind of the depth from a surface, it's not the same, and naturally variation will come. And this is exactly the same thing has been mentioned in this paper, that we require a better one. So what we say, accurate assessment of wear is very crucial to develop a predictive model. We have been thinking about machine learning, artificial intelligence for predictive models, but what will happen in measurement itself is wrong, or we have measured something which is not very reliable, or there is a lot of uncertainty that. And as I mentioned, you look at the wear volume, the sensitivity of H is huge. It is really going to affect severely wear volume. Sensitivity is high. So in the situation, we cannot go ahead with a normal measurement techniques. So that's why we say we require a topography based approaches. So what we say, wherever there is a wear volume is low, because we are aiming for ultra mild wear, we are going ahead with the ultra mild wear, which is very difficult to find out wear rate. And if we don't have a good technique of measurement, sometimes we are measuring a weight, or sometimes we are directly measuring the kind of a wear scar, is it really correct? Because we will not be able to match what we are targeting for better and better results. And if we don't have a measure technique or measurement techniques, then we will not be able to achieve the results. So that's why in this paper they are approaching to the topography based approaches, and I'll be explaining in the next slide. However, they use a slightly different terminology, and they are following G40 ASTM standard. You say we instead, even though we are using the word wear volume, but we need to differentiate. You say in this case, instead of wear, we use two terms. One is called a galling, another one is a wear. What is a galling? In this case, is a surface damage occurs between the two solid surfaces when they are trying to move against each other, and this is a galling is visible by roughening and formation of the raised area, and this is clearly shown in this. What we say, visible roughening, you are able to see that instead of smooth surface we have rough surface, and then there is a formation of the raised area that has been shown here. So it's very clear that whatever wear volume, if we are calculating using the wear scar, that's not going to give a good results to us, and that needs to be differentiated. That's a galling. Now wear, we say wear is generally progressive loss of the material from typological surfaces. So in this paper they are trying to differentiate based on the ASTM G40, and that's why they have given this kind of figure. And they, if you look at this, has been shown here, the portion is a rest, portion is a rest. It's something like happen during addition mechanism where the material is getting transferred. So even that there is no damage, even though material has not been removed from a surface, it's a piled up on the surface itself. So you can see here the surfaces, because of the plastic deformation, is getting displayed or the displaced properly, or maybe that's why that there is a high raised portion, and that has been shown as a green color in this case, while red color material is been removed, that has been shown. So what we say, another important thing which they have done is something, they are identifying the damage of the disc, not a pin. Most of the experiment we use a pin and then we find out what is the damage to pin. because pin is a cheaper. While in this case, just to verify this kind of results, they use a disk and then measure the damage on the disk. And also they are finding the height variation, not volume variation. So they are finding the one coordinate, that's a height, that's a z one. Of course, try to locate the x and y because we really require wear volume and we have a different method. So this is what pin on disk machine. This is the configuration. In this case, the disk is an object which need to be really carefully examined. What will be the wear of this object? Earlier we were talking about the pin or the ball, but in this case we are looking at the disk. So what they have shown also in the figure, the green portion above the reference line, it is a plastic flow or debris deposition. It's a galling phenomena. A material is not been removed. You cannot measure it. It is just piled up, or maybe because of the blowing effect, it has a piled up on one side and other side also. And the red color in this and the below the reference line, there is a reduction of material which can be treated as a wear. So what they are using the word, instead of the wear which has come out, or wear volume which we are measuring, or maybe it's a mass which we are measuring, there that the weight loss will not be accounted there properly. So what is real? Then they are mentioning the cumulative surface damage is a basically overall damage is because of wear as well as a galling. Why they are counting this galling feature? Reason being, it is going to change the component. So that's why we written there, any incremental alteration of a component that involves negative impact on the performance. So slightly variation in a definition. You say any alteration on a surface that involves a negative impact on the performance should be treated as a wear, or maybe say damaged volume. So that's what it will, because it will disrupt the surfaces of the interfaces, it will cause a loss of functionality and leading go for the more and more wear damage. So that should be accounted properly, otherwise we will be getting abrupt results. So this is important. Now coming to the wet loss, why we are rejecting? We say what wet loss method only capable of detecting significant wear. When we are talking ultra mild wear, it is not going to play major role. So that's why it is not suitable for our purposes. When we are thinking of machine learning, we are thinking about artificial intelligence. I can say weight loss method should be completely removed. Another one major issue comes as I mentioned, the resolution of the balance. If you use a resolution 1 milligram is very bad. Even a 10 microgram is not that good. 1 microgram, yes, it makes sense. So it is important what kind of the precision balance is really required. Shall we go ahead with a better one? If you are not able to go ahead with a better resolution, then that should be accounted as some sort of uncertainty, because we will not be able to give a right results. Under uncertainty, whenever we are going for predictive model, we should use that kind of probability distribution. Otherwise, we will not be able to get a good results. Now, whatever we do, we need quite really precise knowledge. Now, here this knowledge is related to the wear volume and the weight. Many times people calculate the weight and they divide by density. Question comes up, do we really have a knowledge of the density? Now, density of object, and many times the people do a composite material and then they divide by density. How? What is possible? Reason being, the material is not a homogeneous. Whenever we use this kind of relation, first thing comes in the material is a homogeneous. Composite material cannot be homogeneous material, right? The reason being, it will have multi phases, and sometimes we are doing a coating or depositing the coating, again we use this kind of weight loss method, it will not be correct. So what I say, weight loss method should be rejected. We should focus only on a wear volume. Again, if we are going for the wear volume, then we again go for the topography, figure out how much is the galling and how much is the wear, and we predict the results based on that. And subsequent all the relation, because as I mentioned earlier, the trapology is a time dependent. As we have mentioned about the in lecture 26, specific wear rate, it depends on the mass and divided by density, and as the material is not a homogeneous, then just dividing by density is not going to give a good result, so it should be rejected. One more thing comes, we in the lecture 13 we covered that even initially the surface roughness is on higher side, and finally it will cause a lesser surface roughness. We will have more valleys and peaks will be torn away. So that was a one case. In this case they are taking another case. So we need to figure out both the cases. Assuming surface roughness, whatever we are giving initially, it will get improved after running in, or tribological conditions may not be 100% correct. So we need to look at both the cases and we need to make it the uncertainty and figure out whether it is really improving it. So it's important. But so what we say in this is we need to give a little more emphasis on volumetric technique, and then possible go ahead with the surface damage measurement. And if it is important, Morales is also there that whenever we are going for surface treatment coating, what will happen, the material will become inhomogeneous. So inhomogeneity should be accounted, and then we go ahead rejecting the mass related technique. We focus only on the volumetric techniques. This is important. Another one, we try to figure out what will be the total damage, and we try to figure out what will be the sensitivity of this damage. If shape is changing, instead of the flat shape it will become the irregular shape, how the performance is going to change significantly. Is it really going to change the tolerances? If it is, then we need to give a lot of emphasis. It is a good for the wear also, and for the gears cases. In gear we know that even slight change or change in the shape or change in the tolerances is going to create more problem. It is also applicable for bearing, it is also applicable for seal, it is applicable for the cam and follower. So most of the tribo surfaces are very sensitive towards the surface damage, or we say the shape variation. Both are the important and we need to account that way. So another one, this paper has mentioned that the stand-up pin on disc technique is limited only. We had to go ahead with the wear volume measurement. As I say, that we are assuming surface will be flat, but it is not. So in reason being, the material may also get transferred from other surfaces, that's possible. And if it is a not we are not able to quantify systematic error properly, then it has a limitation. And just measuring the radius of the wear track may not be correct. Even the variation in radius of the track will also be there. So that's why we really require this kind of analysis, and we say we require more and more topography based volumetric approaches. Use a topography to calculate the volume, and then if we are able to reconstruct one surface, sometime we get a debris and then we are able to reconstruct it, it will enhance really the ability to characterize the surface, analyze the surface appropriately. And then volumetric approaches are really important for us to understand the wear, and in factly we should be utilizing this. So that's why again, as the paper has mentioned, or this research paper is mentioning, topographic analysis is very essential for wear volume calculation. Don't go with a geometry, and don't go directly with a geometry. Try to find out what is that surface profile of that worn out surfaces. Now I'm just going to repeat the one slide from lecture 17. What we say that instantaneous surface roughness influence the tribological behavior. This was earlier we have mentioned that surface roughness plays an important role. Now if we are able to use a machine learning algorithm and in situ observation, that's going to give a very good results to us. This is what was mentioned in lecture 17. We showed in lecture, of course, this was mentioned, and in this paper they are showing the two methods. Either I can really extract the whole surface profile, other one is that we try to measure only the texture parameter. I just explained that. Now if we are able to capture the image, so this was also covered in lecture 22. We say we try to capture the image, we go with gray scaling of that and try to reproduce the image and get all the parameters. That's why we calculate that time SA value, SQ value, skewness value and kurtosis value, and we compare. Once it has been calibrated, then this kind of in situ observation will be providing the wear volume to us also. We can drive it also. How? We will come to that in next slide. In lecture 26 also we say we can really come up with a complete profile. Now if this kind of profile is a measure, we can initially measured or initial value is being given to us, we can duplicate it by importing and doing a necessary MATLAB coding. Once that is done, after that whatever alteration comes because of the wear phenomena, that modeling will be important and that can give a good results. So here we are using image analysis, we are using the MATLAB, machine learning, as well as the domain knowledge. All three together is going to give a very good results to us. In this lecture 26 also we mentioned that how do we go for the better and better filtration. We showed when we are choosing one kind of filter, we are choosing another kind of filter, how this kind of accuracy is improving. So there is a possibility go for the detailed image analysis, go for the detailed writing a code so that we are able to get a measurable parameters from that which can be compared with the measured one, and then we can really systematically analyze one. So in this case, if we are able to do some sort of surface analysis and measure the complete texture before and after the test, what will happen by subtracting these two, we will be able to find out how much material removal has happened or what kind of patch has been removed from a surface. That's possible. Then now we required to implement this in a proper way. Now coming to the prediction of uncertainty, we require many things when we want to go ahead with the prediction of fiction, prediction of the wear. We need to think about what is the uncertainty, how much is uncertainty. So prediction uncertainty involves the potential outcomes and confidence level. That's what already been mentioned. But what are the factors? We need to find out the variability in input data which we are providing, what are the measurement accuracy or errors, and then what kind of the model assumption we have taken that need to be accounted, what is a parameter estimation and environmental parameter as well as the unforeseen parameters. In one go it cannot happen, so you need to have a few iterations to come up with the right results. So that's why we require a multifaceted approach by integrating statistical method, integrating domain knowledge. Domain knowledge is a must, as well as what we have mentioned, uncertainty quantification techniques. As I mentioned, if you are not able to measure the mass lesser than 10 microgram, or we are not able to find better than 0.1, maybe say in this case micrometer, then that need to be accounted so that results are fine so that we can do better fun. And it has to be associated with sensitivity analysis because that is essential for the uncertainty. When we do it, it will really gives adaptability, better resilience, understanding of the system. So like, let me cover another one example. What we say in this paper, they use a physics method, means something like we have a domain knowledge and we are trying to incorporate a domain knowledge with a machine learning. So this is a physics informed digital twin for wind turbine main bearing damage. So they have covered a study on the main bearing damage, and this main bearing is a roller bearing. They have used a roller bearing, and what is the, they try to figure out what is the uncertainty in a grease degradation. So many times when we do a design of the bearing, we select the grease or select the lubricant, that is a beginning, but we know the tribology is a time dependent. Lubricant also will get a degraded. Question comes, are we involving in our models, or we are only gathering the data and going with the data driven approach? So in my case, both the things are wrong. We should start with our own calculation that makes us supervised learning, and then later when the data have been acquired, some sort of correction factor, model factors need to be refined, that will be data driven. So these are the both together, and the hybrid approach is very essential, and same thing has been mentioned in this paper. Why they have done, they found even though what we are thinking about the design calculation, design fatigue life, that was showing some sort of this kind of a life, but actual case they found failure slightly before the actual life, and then they try to diagnose and they found a sensitivity of the surface and the grease degradation is on higher side. So whole paper has been written only on the grease degradation and calculation for the grease degradation. Now here early failure you are able to see here, that is because of the alignment, assembly, manufacturing error, assembly errors. Now After that, they find that because of the lubricant degradation, the bearing becomes susceptible or sensitive to the wear and micropitting. That should be analyzed properly. So what they have done, they use a physics principle, and then why they have used, so the number of data which are really required to make a data driven model are reduced. So that's why I say that decreased data required to calibrate the data driven kernels. And then if they have done only on a data driven model, it will have a problem related to the knowledge, and it will give something different results. I'll show you the one of the figure which they have given. If you go only with the data driven model, what will be the results? Now, before going to that, let me explain little bit about the rolling element bearing. This is a rolling element bearing kind of the pittings. So we are able to see pits over here. It's a natural life. In this case, particularly, I analyze after 40,000 hours of the bearing. So it is a natural one. And then when we go for the rolling element bearing, they find out the bearing life in hours using this kind of relation. This is a capacity which has been given in catalog. This is the applied load, and this is the RPM at which it runs. So this is a what equation is generally being used. We generally assume 90% of the reliability, and then calculation is based on the 90%. However, somebody say I want only 50% reliability, they can use this kind of formula, and we if you substitute the values, you will find the 50% reliability will be the almost life will be almost 5 times compared to the 10% reliability. So that reliability itself can be one of the parameters. Somebody wants a 99%, that also can be calculated using this. These authors also mention that when we think about the grease, and then as one of the very sensitive parameter, important parameter, so they are trying to analyze each and everything from grease point of view, and then mention that as the temperature increases, naturally the grease quality will decrease. Not only this, and it is also getting affected with the reliability. So that's the what they are showing. Reliability 50%, then the black color line reliability 10 sorry, life reliability, when say L10, that means we have a 90% reliability, and this is a 50% reliability. So this is a L10, 90% reliability. L50 is a 50% reliability. And then when we go ahead with the factors, these are the some factors, maybe K1, K2, K3, K4. Now depends whether the factor is really increasing the bearing life or decreasing the bearing life. So sensitivity done is a done. If it is a positive, naturally it will be in proportion. If it is a negative, then it will go in a denominator. So those factors also can be calibrated or can be rearranged appropriately. So coming back to this paper, they examine the uncertainty caused by the grease, and then they say that what are the mechanism of the degradation, what is how do we do inspection, how do we quantify the grease is really getting damaged, and then what will be the overall the quality assurance about that. So they have done, and then they have mentioned also related to some sort of quantification. They give a bad grease as a rating 5, very good grease as a rating 1, which is some extent subjective. And then we can also really devise number of parameter to go ahead with a grease quantification. We have many parameters. Of course, in this paper they have shown a kind of subjective knowledge. So what we are seeing is standard bearing life calculation are valuable. So that's why they are using the equations which are really providing initial support. But these equations are not reliable. Reason being, they are when the actual situation comes, actual operating load comes, operating condition comes, then this grease variation will occur, grease degradation will change. So we really require rules and regulations when we go for the data driven models, which is a black box. We will not be able to get much from that. It will do a lot of calculation. So we really require support from formulas which we are thinking using. So that's why we say the physics based models provide understanding of output. Of course it has an inherent shortcoming. So whatever the shortcoming of the physics based formula, that can be fulfilled by the data driven, and whatever the drawback of the data driven model, that can be fulfilled from the physics based model. That's why they are using a hybrid technique, and that's what has been shown, the hybrid technique. integrates a physics-based models which are really required initial values to be given to the model parameters, and data-driven kernels to tackle the challenges which is generally caused by variable grease. So here only they are focusing more on a grease quality, not a misalignment, not other parameters. How the grease quality is impacting the bearing life as such. So they require overall lesser database, and then they again to reduce uncertainty, they have used a pre-trained networks, because when we do our own coding we again need to train it, but if there are already pre-trained network layers are available, then uncertainty to some extent will decrease. That's what they have mentioned. Now this is what we say that they have done a grade 1 new grease, the good grease, grade 5 the bad grease, and then they say they go ahead with the baseline inspection and conservative inspection, and they define the what is a baseline inspection. We say generally it is done by the technician uh, who have a tacit knowledge, we have understanding. They found that many times there is some sort of variation, and then they find many times we say viscosity variation itself can give us some sort of a justification whether it is a grease getting degraded or not. That's also possible. However, coming to the conservative side, generally technician gave a wrong information, like grease quality is still good, but they will declare the grease quality is bad, better replace it. It is a conservative side, so the bearing should not get damaged, and that has been tabulated here. You can see the baseline information which they are doing with the visual inspection. The green good is a 70%, second quality 30%. Here the after when the actual damage is a 20%, they are the 10% damage they are showing as a very good grease good, and 40% really the bad grease to some extent, 30% moderate, and then these are going on a worse side. So as the damage increases, you can see here when the 80% damage they are showing 80 and 20%. So this is a baseline. But coming to the conservative side, they are showing little more degradation to the grease. You can see here there is a 100% damage here instead of 20 and 80. Here in the 50, 30, 20 something, while here they are showing 80 and 20. So this is a conservative. Now when we plot it, we are able to find that baseline information is real near to the what we are able to predict the right values, but conservative is a little away. So most of the time people or the technician follow the conservative design. The grease is good, still they replace it, which may not be really required. It will be the little costly because we need to re-grease bearings, and which may not be really requiring it. So that's why the this kind of inspection is important, and then we really require to go ahead with the better results. And then they also showed one of the way to see is a when the temperature is increasing, what will be the viscosity difference. You look at the new grease, viscosity is on higher side, degraded grease is a lower side, and viscosity measurement of the lubricant is not that difficult. We can use a rheometer, we can figure out, and we can find out with the temperature, with the number of cycles, how the viscosity is going to change. So based on that, they have found some sort of a contamination factor, which as I mentioned in when they are applying to the bearing life, they use this kind of factor. The factor is on the higher side, the factor is on the lower side. So this is when we multiply lower side factor, the bearing life will be lesser compared to the new one. So this is what they have done, and this is the final thing which I'm showing. They have used a long short term memory LSTM network, and then is a pre-trained network they have used. They are showing that they have used a shallow LSTM and deep LSTM. Of course, in deep LSTM, when they mention they are using only 3 layers, so it's not a many. When they use a shallow, they are using only 1 layer. Number of neurons they have used 8 and 8. Number of parameters selected with 360 and 1448. Now this is the comparison they have showed. When they are going for the shallow or deep, you can see the behavior. This is the behavior of the shallow and deep, and then these are the actual cases, dots, observations. And then when they are going with this physics informed neural network, it is showing a better results in this case. So they find when we go for hybrid model, we use our knowledge, domain knowledge, and we also use a machine learning knowledge, it will give better predictability compared to the only data driven model. So I can say the shallow LSTM is a data driven model, deep LSTM is a data driven model. They are not giving good results, but this physics based informed neural network gives a better results, and then comparable results compared to what we are observing it. So that is what we should be doing. And this sensitivity analysis and uncertainty quantification helps us to understand how to improve the model, how do we improve the measurement technique. Like in this case we mentioned very clearly where volume can be measured, but if the topography method, that will give always a better results compared to the where volume, and which is generally derived from a mass calculation, because mass calculation itself gives a wrong results. It has a number of limitation, and then if we are drawing a volume from that, it will have further limitation. While calculation, volume calculation directly from a measured dimension may not give a very good result. So better go for the micro to nano level, find out the details. Maybe we'll compare the surface roughness parameter, which R45, and then get a good results. And this is very important. With this, I say thank you for attending this lecture. Thank you.